So today we want to start with hyperbolic functions. These functions actually arose as a result of the fact that you have the exponential functions occurring frequently in certain expressions in mathematics, engineering, physics, and other fields. And so there's a theory that says that given any function, you can write it as the sum of an even and an odd function. So for instance, e to the x, we can rewrite this. We can write this as e to the x plus e to the minus x over 2. We can add this to e to the x minus e to the negative x over 2. You can check that when you add this up, you get the exponential function. So this function is even. It's an even function. And that is an odd function. Okay. Now the even parts, okay, of that exponential function is called the cosine, the hyperbolic cosine function, like cos x, and then this is the hyperbolic sine function sin x. Okay, which means that I can actually write the exponential function as cos x plus sine x. And so by definition, the so-called cos hyperbolic or hyperbolic cosine function cos x is given by e to the x plus e to the minus x divided by 2, and sine x is given by e to the x minus e to the minus x divided by 2. So these two functions are two of 6 hyperbolic functions that we need to know. Okay, so that's the definition for the cos and sine. The third one is given by the tangent hyperbolic function. Okay, so the hyperbolic tangent function, which is the quotient of sine and cos x. And just like you have for the trig functions, the reciprocals of these functions also give you additional 3 hyperbolic functions. So the hyperbolic second function is 1 over the cos x. The hyperbolic cosec function is 1 over the sine x. And then the cos x is 1 over x. So 6 hyperbolic functions that you need to be aware of. Number 1, number 2, like 3, 4, 5, 6. 6 functions that you should note. Okay. And of course, you can always rewrite all these functions in terms of the exponential function. That is what is neat about these functions. Good. So how do they look like? We'll go and look at, we'll take a look at the graphs of these hyperbolic functions. Because they are exponential functions, one way you sketch them is to use a sketch of the exponentials. So for instance, the hyperbolic cosine function, cos x, is given by e to the x plus e to the negative x all over 2. So we could actually combine the graphs of e to the x over 2, e to the negative x over 2, combine those two to give us the graph for the cos x. So for instance, let's draw this like x and y axis. The exponential function is given by that. If you like, this is e to the x over 2, half of that. At 0, e to the x is 1, so this guy is at half. Okay? And then e to the negative, look at this is e to the x over 2, e to the negative x over 2. This guy is given by x. So this is e to the 1/2, like e to the negative x. So the sum of these two graphs should give me the graph of the cos hyperbolic function. So how do you add that up? Well, this is a half and a half. If I add half and a half, that gives me 1. So it means that the hyperbolic cosine function starts from half. Now note that as x goes to infinity, this guy is approaching 0. So then this is going this way. This is going to 0. So as x goes to infinity, the graph is dominated, right? This guy has become dominant. So as x goes to infinity, this guy goes like that. As x goes to negative infinity, this guy goes to 0. And so this is dominant. So at negative infinity, this guy is dominant. And that gives you the graph of the hyperbolic cos function. So that gives us a sketch of cos x. You can do a similar thing for the graph of the hyperbolic sine function. So here we can also sketch it. Such action is given by e to the x minus e to the minus x over 2, which means I can rewrite this as 1/2 e to the x, like plus the negative 1/2 e to the negative x. So I can sketch the graphs of this, the graph of minus half of e to the minus x, add the 2 as I did for this, and then you get a graph for the sine x. So you have this. Again, e to the 1/2 e to the x is that. Yes, function. And again, this is 1/2. That is 1/2 e to the x. Note that e to the minus x is a graph that goes like that. Now it is negated. Okay, we negate it. So which means that the negative 1/2 of e to the negative x is a graph that goes like so. Okay, so this guy here is like negative 1/2 e to the negative x. So basically you have to add these two graphs, and that should give you the graph for the hyperbolic sine function. So how do you do that? Now this causes 1/2 here. So if x is 0, if I add these two, I get 0, which means the hyperbolic sine crosses 0. Now as we did for this, as x goes to infinity, positive infinity, this guy goes to 0. This is vanishing, and this is more dominant. So as x goes to positive infinity, the graph approaches that of this. So as x goes to infinity, expect the graph of the hyperbolic sine to do this. And as x goes to negative infinity, this guy vanishes until the graph approaches this guy. This graph. So it goes like that. So this gives us the graph of the hyperbolic sine function. Okay? So be familiar with the graphs of the hyperbolic cosine and then the graphs of the hyperbolic sine functions. You can do a similar thing. I'm not going to go into the details, but you can do a similar thing for the hyperbolic tangent function. Alright, and that is given by this graph. So the y equals tangent x. That is given by this. You can actually use the fact that you can write this as sine over cos to get e to the x minus e to the negative x over e to the x plus e to the negative x. This we can rewrite, right? We can rewrite this if I multiply the top and bottom by e to the x. This will give me e to the 2x minus, this is 1. This gives me e to the 2x. This is plus 1. Or if I multiply the top and bottom by e to the negative x, I get 1 minus e to the negative 2x. And I have 1 here plus e to the positive negative 2x. Now each of these will help us to see different aspects of the graph. Okay, so what you notice that as x goes to positive infinity, as x goes to infinity, if you use this expression, this guy goes to 0, that goes to 0, and so this approaches 1. So times x will approach 1 because this goes to 0 and that goes to 0. And as x goes to negative infinity, now we can use this. This goes to 0, that goes to 0, so you have negative 1 over 1, which is negative 1. So times x approaches negative 1 as x goes to minus infinity. So at positive infinity, it approaches 1. At negative infinity, it approaches negative 1. You can show that it crosses here. Okay, when x is 0, it is 0. You can check that from here. This becomes 1 and 1. 1 minus 1 is 0. That is 2. So it is 0 here, crosses this. As x goes to infinity, it's going to approach this. So it's doing something like this. As x goes to negative infinity, it's approaching negative 1, as we just showed there. So it goes like so. So that is the graph of hyperbolic tangent function. Alright? So at least these three, but be familiar with these three hyperbolic functions and their graphs: the cosh, the tanch, and then the sine functions. Okay. Good. Now next, we want to look at some properties of these hyperbolic functions. We'll show a few properties of them. So here, some identities of hyperbolic functions. Okay, so here are a couple of them. We should prove some of them. First one says that sine minus x is negative sine x. B says cosh minus x is cosh x. And then prove this: cosh squared x minus sine squared x is equal to 1. Okay. We have a couple of them. We'll illustrate them by this. So I'm going to do this and that, then you can try this one. It's easy to prove. So we're going to use the definitions of these hyperbolic functions based on the exponentials to prove these ones. Okay. So here, the first one, we have sine. We know the definition. By definition, this is given by a to the x minus a to the negative x over 2, which implies that sine, if I take a negative x, replace every x with a negative x, and that gives you e to the, this is minus x. Negative x here gives me a positive x over 2. I can rewrite this, but pull out the negative, I can rewrite this as e to the x, and the positive minus e to the negative x divided by 2. But this guy here is sine x, so this is negative sine of x. And that is the proof for A, the first one. Okay? I'll skip this and then I'll prove this one. This is very important. You can get other relationships from this one. So here, let's do this one. We want to show that cosh squared x minus sine squared x is equal to 1. So we're going to do this based on the definitions. Cosh squared x minus sine squared x. This is equal to, by definition, cosh is e to the x plus e to the negative x over 2. I'm going to square this. I have minus. I have, by definition, sine is e to the x minus e to the minus x over 2. I'm going to square this. So manipulate this to see whether you get 1. That's the idea. So this is equal to, square this. This gives me e to the 2x plus 2, and I multiply this out, and then plus e to the negative 2x all over, this is a 4, when I square the 2, minus, this guy gives me e to the x, 2x, the 2 of them gives me minus 2, this is a plus e to the negative 2x all over 4. Okay? So we can simplify this, we can rewrite this as, if you like, I have e to the 2x, okay, and I have plus e to the minus 2x, okay, all over 4. I have this guy, which is 2 over 4, and then if I do this, this is 1 minus this, and this guy gives me e to the 2x, that's e to the minus 2x, okay, all over 4, and then this and this guy gives me, be careful here, this cancels this, so you have 1 this, and I have plus, okay, 2 over 4. Alright, so we have e to the, note this, you can put this in brackets if you want. Okay, so note we just expanded this and expanded that, that gives us this and this. Note that this guy in brackets is the same as what is in brackets here, but this is negated, so this cancels out this. So this guy and this cancels out, and have a half and a half. So we get so what we have is that we have cos squared x minus sine squared x is equal to, this is 1/2, and that is 1/2, and that is equal to 1. So we have proved the relationship. Okay? So that is often how you prove these hyperbolic relationships. You can do one that is a bit different from this, and then we'll move on to the next section. So here, okay, let's do this one. It's a particular one. We want to show that this, like this 1 minus sine squared x, to prove this. So what you're doing is because I want to show that you can use the previous relation we just proved to get this one. Okay? So I want to show this. How do you prove it? Okay? Recall or remember that we said cos squared x and sine squared x. We just proved that is equal to 1. How do we get this one? Okay, now sec is 1 over cos. So all you do is you can divide through by cos squared. Okay, so divide through cos squared x. And this gives me 1 minus sine squared over cos squared x is equal to 1 over x. This implies that we're going to have 1 minus sine over cos sine. So this is the hyperbolic term squared x. And then 1 over cos is secant, so that is secant squared x, which is the relationship we wanted to prove. So you can often use this to prove several of the other identities. Hyperbolic identities using this one. Okay. Let's move on to the relationship to the exponential function. Relationship to the exponential function. Prove this. Now recall that when we started, we said that the exponential function, we can write it as the even part of it was the hyperbolic cosine, and the odd part was the hyperbolic sine function. And then we can also write e to the negative x by replacing x with negative x as, and because this is even, if I plug negative x, I still get cos x. This is odd, so if I put negative x here, I get minus sine x. Okay. So these are two relationships that we have: the relation between the exponential and then the hyperbolic functions. Okay. Now you can further go ahead to show that the hyperbolic functions are related to the trigonometric functions, which is easy to see. Now you see that these guys resemble the Euler's formulas from trigonometry, right? From Euler's, we call Euler's formula from straight or complex numbers. E to the minus x was equal to cosine of x plus I sine x, and then of course you can then write e to the minus x as cos x minus I sine x. You can call this equation 1, you can call this equation 2. Okay. So we see how the hyperbolic functions are related to the trigonometric functions. Now if I add these two equations, if I have 1 plus 2, if I add them, these guys cancel out. This is positive and that is negative. This and this will give me 2 cos x. And I have this plus that. That gives me e to the ix plus e to the minus ix. Which implies that cosine of x is e to the ix plus e to the minus ix all over 2. But this we recognize to be the hyperbolic cosine function, which implies I can actually write cosine of x to be equal to, this becomes cos I x. See there. The trig function is related to the hyperbolic function here. Again, if I subtract, if I take I minus equation 1 minus equation 2, what do I get? These guys cancel out. This and this will give me 2I sine x. And that is equal to e to the ix minus e to the minus ix. If I divide 2 by 2I, I get sine x is equal to e to the ix, e to the minus ix divided by 2I. Okay? Now, if you multiply the top and bottom by I and I is I squared, which is negative 1. So this is actually equal to minus I multiplied by e to the ix, e to the minus ix all over 2. Okay? But this guy is a hyperbolic sine with argument ix, which implies that I can write sine x to be equal to negative I sine ix. And that is another relationship between the trig function and the hyperbolic functions.